We spent some time over the last couple of days looking at diffraction gratings. And by diffraction grating, I mean some kind of barrier with openings. Maybe it's 2 openings, maybe it's 10 openings, maybe it's 1,000 openings. It doesn't really matter. The pattern that we end up seeing is almost the same. Let's say in this case we have 2 openings. Light goes through these 2 openings, diffracts through both of them, and then interferes and forms an interference pattern on this screen over here. Let's say that we have red light, red laser light that's going through there. Monochromatic. What does monochromatic mean? One color. So just red laser light going through these 2 openings. When it diffracts and interferes, it forms a pattern that looks like this. We have a bright spot, and then we have well, we call it a dark spot, but it's the absence of a bright spot. Then another bright spot, then another dark spot, and so on both sides. We would call this our central maximum, our central bright spot, our central antinode. We would assign a number of 0 to it. The one beside it we would call our first order maximum, and same on the other side. Our second order maximum, same on the other side. Now, these things in between, these minima, where we have dark spots or the absence of bright spots, those are going to be assigned numbers of, what's that first one? The first order minimum is 0.5. And the second order minimum is 1.5, and so on and so on and so on. Now, let's identify some of the other variables here. What is this distance between these 2 openings called? The slit width. What variable, I should say, is that? That's little d, right? Little d is the distance between the slits. Now, sometimes we're not given a little d, or we're not asked to solve for a little d. Rather, we're asked not to find the meters between openings. Rather, we're asked to find the lines per meter. In other words, the inverse of that. So as opposed to d, sometimes we've got, or asked to solve for, 1 over d. Remember, lines, or, centimeters or meters, d, lines per centimeter, lines per meter, it's 1 over d. Nice and easy to convert them. You just flip it over, right, to get little d. What's this distance right here called? The distance from the screen to the openings? This is capital L. Well, I write it as capital L. On your data sheet, it says a little l. I just don't want to get mixed up with a 1 there, so I write it as a capital. What about this one right here? When we want to find the distance from the second order maximum to the central maximum, or we want to find the distance from second order minimum on one side to the, let's go the second order maximum on the other side. Just gave it away. What's that variable called? Yeah, it's called x. So x is a distance measured usually in meters, and not some kind of counting or not some kind of numbers or subtracting. It's just the distance. Physically take a ruler, measure the distance between those. So if Ariel uses this x, okay, and Connor uses this x, how do they both get the same answer for the question? Yeah, because of n, right? N has to be consistent with x. What would n be? Let's do this one first here. What would n be for this first one here? From the central maximum to the second order maximum, n would be 2. Good. And for this one, we got from the second max on one side to the second min on the other side. What would n be? That's a trickier one. We're going from 1.5 on one side to 2 on the other. N would be 3.5. Doesn't matter what you use here for x. Use whatever's given to you. As long as n is consistent with that, you should get the right answer. Now, there's one more variable here, and that's theta. Theta is always measured from the central max to, the second order max, or from the central max to the, let's go the second order min. Doesn't really matter, as long as it's from the central max, and as long as n is consistent with it, right? What would n be in the first case here when we're going from 0 to 2? What would it be? 2, good. And what would it be in the second case when we're going from the first central maximum to the second order minimum? Ryan, what would n be in that case? Central to the second minimum right here. Good. N would be 1.5 in that case. So it doesn't matter what you're using, as long as n is consistent with that. Good? Let me draw another picture that's similar to this, but we're going to use it for a slightly different purpose here. Let's once again shine red light through there, monochromatic red light. When we do that, we get an interference pattern that looks like this. Central maximum, first order maximum, second order maximum, and so on, as far as we want to end up going there. Make sense? Nothing new there. Let's change the color though. Instead of having red light go through there, let's put blue light through there. If I shine blue light through there, it's going to diffract as well, and it's going to interfere as well. The central maximum for blue light will be where the central maximum for red light was. The first order and the second order maximum won't be. Remember those two equations that I taught you the other day? Lambda is equal to d sine theta over n. Lambda is equal to xd over n times L. If, this was our if equation, if theta is less than 10 degrees. Or we can use our rule of thumb, or our ROT, and say that we can use this equation if L is greater than 10 times x, right? We're going to use this second equation here. We're not using any numbers, so we don't have to worry about the rule of thumb. The relationship, the proportionality holds no matter what the numbers are. You can't calculate anything with that equation unless theta is less than 10 degrees, but the relationship, the proportionality will still hold. So let's look at this equation. Recognize that lambda and x are directly proportional to each other. Now, when I go from red light to blue light, what's happening to lambda? Am I increasing lambda or decreasing lambda? What is it? What is it? I'm increasing, when I go from red to blue, I'm increasing not the wavelength, but the frequency, increasing frequency. So what's happening to the wavelength? Decreasing, right. Increasing frequency, decreasing wavelength. So as I go from red to blue, the wavelength is decreasing. Got it? If the wavelength is decreasing, then what's going to happen to the value of x? It's going to decrease, right? As lambda decreases, x decreases. So what am I going to see over here for blue? Blue is going to be closer together. The maxima will be closer together than they were for red. Does that make sense? Green would be somewhere in between, right? Because green has a wavelength that's in between red and blue. What if, though, what if I shine both of these colors at the same time? Not one at a time, not monochromatic light, but shine blue and red through it at the same time? Well, you're going to see red and blue. It's going to split up, just like it did with, remember the Pink Floyd, Dark Side of the Moon, the prism, when we had dispersion, white light split up because different colors refracted differently. Well, different colors diffract differently as well. We will see in this case something that looks like this. We'll see a central maximum that has red and blue combined. We will see a first order maximum that has red and blue separated because blue didn't diffract as much. We have a second order maximum, same type of thing. First order maximum, second order maximum, and so on and so on and so on. Now, again, if we had green, green would be in between, right? So what's happening here? Almost the same thing has happened with the prism, right? The prism split up white light into Roy G. Biv. The diffraction grating splits up light, not because of refraction, but because of diffraction, not into Roy G. Biv, but into what comes first? Not red, orange, yellow, but, yeah. Okay, just a sec here. Not red, orange, yellow, but rather violet, indigo, blue. It's backwards, right? Look at the poster on the side of the room. Red refracts the least. Look at the picture up on the front of the wall. Red diffracts the most. But with a prism, we get a single continuous spectrum, a single rainbow. What do we get here? A rainbow, and then another rainbow, and then another rainbow, and then another rainbow. We get continuous, multiple continuous spectra, multiple rainbows formed there. With, by the way, in the middle there, if you had multiple colors, this would just appear as white light because it would be all of the colors combining there. Now, if you happen to get a question, let me rephrase that. On next Wednesday's test, when you get a question that involves multiple colors, don't let that bother you. If you get multiple colors, what I want you to do is just pick one. If you have data for blue, just pretend that red doesn't exist. Erase it. And just use your data for blue. If you have data for red, then pretend that blue doesn't exist. Does that make sense? You're going to get a question, right? I effectively just told you. You're going to get a question where you have, let's say, my central maximum. Okay, this is my central maximum, which is white light. And then you get something that looks like this. And you're given information for, let's say green. Okay, you're given information for green. Maybe the wavelength, whatever. You're given information for green. People are going to try to analyze this. Some of you guys, prove me wrong, but some of you guys, I think, are going to try to analyze this, saying, look, this is 0. This is a first order max, right? 1, 2, 3, 4, 5, 6. If you're dealing with this and this, some of you are going to try to make n equal to 5. What should n be equal to? What should it be? 2. Because remember, if you're analyzing green, as far as you're concerned, the other ones don't exist. Got it? This wouldn't be 2 and 5. This would be 1 and 2. N wouldn't be 5. N would be 2. So we'll look at practice question set number 24 that relates to this stuff of diffraction interference. First one, we have a microwave generator. Usually we have visible light. This time it's microwaves, not a big deal. Used to produce a beam of monochromatic microwaves. In other words, one color microwaves, one frequency microwaves. We know what to do if we have more than one frequency, but one frequency just eliminates confusion for us. So that's good, one frequency. The waves are incident on a series of metal tubes that forms a diffraction grating. The metal tubes are spaced 1.8 centimeters apart. Tell me what that corresponds to. What variable is that? That 1.8 centimeters. Is that L, D? Is that X? Is that N? Is that theta? What is it? Zach, what is it? Yeah, it's a little d. Little d is 1.80 centimeters. Now, usually we're in meters here, but we'll worry about that a little bit later on here. Tells me as well that the angle from the central maximum right here to the first order maximum right here is 49.8 degrees. Now, it's 49.8 degrees to the first order maximum on the other side as well. But we don't need both of them, right? Theta is 49.8 degrees. What would the value of n be that's consistent with that 49.8? 1. Yeah, we're talking about from the central to the first maximum on either side, n is going to be equal to 1. Now, we're looking for the wavelength in this question here. Lambda is equal to d sine theta over n. It's a good thing that we have theta, because in this question, clearly we're way above 10 degrees. We couldn't even begin to think about using the other equation here. D is, do I have to convert that? Well, usually we do, but as it turns out, we don't actually have to, as long as we're consistent. If we go centimeters here, then that's okay, as long as we recognize that lambda is going to be in centimeters, which is what we actually want our answer to be in here. So I'd probably just leave it here. 1.8 times sine 49.8 degrees over 1. That gives us a value, I believe it was 1.37. Does that sound right? 1.37 centimeters. So I'm going to fill this in as just 1.37. Now the second question is a qualitative question. We got 8 different observations. We want to know which of these 4 observations could be produced using a triangular glass prism. I don't like that word only in there. I'm just going to make it which 4 observations could be produced using a triangular glass prism. Let's look at these different observations here now. A continuous spectrum is like a rainbow. Could a prism produce a rainbow? Yes. Yes, it could. A bright line spectrum, we haven't really learned about a bright line spectrum yet. We do learn about it in our next unit, our last unit. Bright line spectrum is just not a rainbow, but rather a line, a distinct line, and then another distinct line, and then another distinct line. You'll see where that comes from in our next unit. But the bottom line is, if you haven't learned about it yet, it's not the answer. So we get a continuous spectrum produced by a prism, not a bright line spectrum. Does a prism produce an interference pattern with one color of light? Does that produce an interference pattern over there on the wall? No, there's no interference pattern there. Does the apparatus produce a single bright line with monochromatic light? In other words, if I have a prism and I shine one color through that prism, do we get a single bright spot over here? Yes. Yes. Right, one color goes through, we get a single spot on the other side. The only reason we have multiple colors on that poster over there is because it's not monochromatic light going through, right? It's white light going through. Bends red light smaller than it bends the blue light. Does the prism bend red light smaller? Yes. So that's going to be a prism. Then it therefore can't bend red light larger. How would I change this question to make 6 correct? Which of the following could be produced not by a prism, but a diffraction grating? Because diffraction gratings bend red light more than blue. Prisms bend red light less than blue. The apparatus produces a single spectrum when white light is incident on it. Do we get one rainbow over here? This dark side of the moon poster? Is this one spectrum? Yes. We get a single spectrum produced by a prism versus number 8, multiple spectra. Multiple spectra would be produced by a diffraction grating, right? We get the first order maximum that is a rainbow, but opposite order. The second order maximum that is a rainbow, but opposite order, and so on and so on.
Like, wouldn't that just make one light light?